Can nuclear energy be small and modular? That's what I want to answer today on Science Spotlight 8, Small Modular Nuclear Reactors. I'm Dr. Mark Williamson. Let's get started. To cover the topic of small modular reactors, I want to start with a 2021 report called Small Modular Reactors, Challenges and Opportunities, which I think gives a good overview of the concept. So, they define small modular reactors, or SMRs, as nuclear reactors with power outputs of 10 to 300 megawatts electric. What that means, sort of practically for power, about 1 megawatt electric can power about 200 to 800 homes, depending on the power source and reliability. Nuclear is at the upper end, so ballparking probably about 700 houses. So 700 houses per megawatt electric. So we're talking thousands of houses with small modular reactors. So they're small, but not that small. Small only in comparison to, say, typical nuclear reactors, which maybe have 10 to 12 times the output. So, next, uh, back in 2021, there are over 7D small modular reactor concepts under development. So there's a lot of different concepts trying to be worked out, developed, and put into action. Now, the idea of small reactors, nuclear reactors, is not new. They've actually been used since the 1950s in government, like, for example, nuclear submarines. Now, there are some different constraints and details that go into that, but having a smaller nuclear reactor is not a novel idea. Now, there are several categories. Again, there's a lot of different concepts. So this overview does help break it down into some conceptual categories. First of all, there's the single unit LWR, or light water reactor, small modular reactors. So these are essentially scaled down versions of the typical nuclear reactor, which almost about 90% of those are light water reactors. You could have a multi-module light water reactor, so they're meant to chain together, hence the modular part of it. You can also have mobile or transportable small modular reactors, like putting that on a barge, putting it on a ship, etc. You can have what's called the Gen 4 small modular reactors. These are very experimental, looking at different things than water for coolants, other configurations. So they're certainly experimental. There aren't any, they don't have a direct analog to currently operating large reactors. And then there's a class called micro modular reactors, MMRs, or just microreactors, which are even smaller. They're on the smallest end of this small modular reactors. Now, one of the big things that developers of these small modular reactors have to come up against is that large reactors benefit from what's called economies of scale, where as small modular reactors to actually be economically viable, they need to benefit from economies of series. That is, you can build a lot more of them in a more series-like manner, like building them at a factory and then shipping them out, rather than building one huge reactor in one place. So just as like aircraft have benefited from economies of series and other industries, small modular reactors would need to take advantage of that to make them viable. Now, there are some serious advantages to small modular reactors, especially compared to large reactors. They have integral designs, they have inherent safety, they have low core inventory, so they're smaller, less nuclear fuel. They have improved modularity and manufacturability, and they have enhanced flexibility. Now, some serious challenges that need to be overcome is licensing. A lot of these, especially the more experimental ones, don't have any analog in the real world, so they need to be. There's a lot of complexity in trying to deal with that, unfortunately. There's also the technology type. Because there's so many different concepts, designs under choice, under development, it's hard to tell which one is the right one to back. And so I think investing in it's hard because you're not sure what will shake out until some of the technology is more mature. And then, of course, there's technical uncertainties of how they'll work, what long-term operation might mean for some of these more experimental devices. And there's supply chain and fuel issues. And finally, public perception. Unfortunately, despite nuclear energy being very safe and clean, a lot of people don't like it. And this overview kind of concludes with commercial viability being in the early 2030s, because at the time of this article, there are really no small modular reactors in operation, with one exception we'll talk about, and there are only a few under construction. Now, a lot of the major players in the area when it comes to countries, that's going to be Canada, China. China notably actually has some at that time of this article under construction. France, Russia, which is a very interesting, notable exception to the actual in production. The UK and the United States. Of course, there's other places like Korea, Japan, but these were the six that this overview talked about. Now, the notable difference I want to say, again, going back to Russia, they actually have a small modular reactor of the mobile or transportable type. It's actually based on a ship called the Academic Lomonosov. Now, it's not powering the ship, but the ship has a reactor on board and it can like dock and then supply energy to the shoreline. And so that's actually under operation. So that's one of the few examples. Now, this article had this good table of different conceptual designs of the different types. So like there's the single units up here, the multi units, the mobile, and most of them are just design. There is one apparently under construction in Argentina, but then the big ones that were under construction are going to be coming out of China, and then the Russia, of course, having one of those mobile ones with commercial operation. And then here's more of the Gen 4. There is one under construction in China, but everything else is just a design. And then there are none for the micro reactors that are actually under construction or in operation. So that comes back to a really important point of these small modular reactors is, okay, you can get the technology to work, but is it economically viable? Like, will people invest lots of money to actually use these to generate energy? Are they a good bet? So there's this paper here called Economic Viability of Light Water Small Modular Reactors, General Methodology and Vendor Data. So this is just looking at the more mature version, and asking the question, are small modular reactors economically viable? And so they looked at one concept. It's from the company NuScale. And so this is a light water reactor. So it's, again, sort of a scaled down version of large reactors that are already in operation. So they compared a standard nuclear reactor, a Power 12, versus a NuScale modules, 12 of them, so that similar megawatt electricity output. They calculated capitalized direct costs, capitalized indirect costs, and base construction costs. And now, based on both absolute basis and per kilowatt basis, the small modular reactor was actually significantly less expensive. And they broke it down to specific categories, the main ones being bolded. Now, let's just look at the kilowatt cost per kilowatt table a little closer. And so there's a NuScale cost, the power cost, and then the cost difference. And so in almost every case, other than the reactor plant equipment and field construction management, the NuScale was less expensive. So it does look like at least the more mature light water reactors there are economically viable based on this research. Now, we've talked broadly about what they are and a little bit about the economics. Let's go into like some more specifics of like who's actually making them and who's prototyping them. So I got a list from smallmodularreactors.org. It's fairly informal, but gave a list of different companies that are developing these, and then their main reactor. And so I was able to follow through and look through several of these to get more detail on the actual company's website, just to get a taste of what is out there. So first of all, there's the NuScale. That's one of the more mature. It has the NuScale power module. So these are light water reactors, kind of set up here. Looks like the main operational objective is 60 years, so that's pretty good. The electrical power per module is 77 megawatt electricity. And so, if you chain about 12 of those, you get a conventional large power plant. Then there's the Holtec International, the SMR 300. I really couldn't get too much. I just got this reactor cooling system from one of their, I think, white papers. There's the GE High-Tech Haiichi Nuclear Energy, the BWRX 300. Again, it's another boiling water. It looks very similar to the new scale, that kind of design, the large sort of cylinder. It's 60 years. It does say these ones looks like they're larger, 300 megawatt electricity. And then there's like Natrium by TerraPower. Wasn't clear exactly what the design was, but they're actually building a plant in the mountain west of the U.S. For scaling and developing this. So that looks like that's moving forward. All right, some other companies. There's General Atomics, which actually has an energy multiplier module, which is kind of interesting, where it has one here. You start with certain kinds of fuel, and you can actually take some of those fuel byproducts and actually run it through a second generation of use nuclear fuel to produce more energy, and so on and so forth. So that's very interesting. There's the X Energy, the XE100. So these are actually, I think, like gas cooled. So gas cooled, and it has this pebble bed setup with trisol fuel, and we'll talk more about trisol fuel. Then there's Rolls-Royce has an SMR concept. Now, I couldn't find any actual pictures of the concept, but they had a nice image of just generally what it looks like conceptually for a nuclear reactor. You have the control rods, the coolant, steam generation, electricity, condensation, etc. And then there's Oklo, the Aurora. Looks very similar to something like the new scale, so I bet it's a light water reactor. Then going to some of the more Gen 4, we have Moltex Energy, which actually is a salt reactor. So it uses molten salt as coolant. There's U Battery, which, again, I'm not sure if it's molten salt or gas. Yeah, exactly. But again, uses trisol fuel, and this is probably a good place to talk about trisol fuel. So trisol fuel is there's a fuel kernel with like uranium or uranium compound, and actually it's coated by three different layers. That's like the trisol part of it. And then that can be either in those balls, and you can put it in a pebble bed, or you can actually insert it in something like a graphite block and use it more like a control rods, like a traditional reactor. And so trisol is a pretty common fuel setup for these systems, whether by itself or embedded. There's Seaborg Technologies has a compact molten salt reactor, the CMSR, again using molten salt. Thorcon has a molten salt reactor as well. So with Moltex Energy, they had a nice little diagram. Again, I kind of like seeing some of this conceptual diagram of having a reactor core. You have molten salt fuel. Obviously you're heating things up. You're having heat exchange. You're powering things to get electricity, and you can even get heat. Yeah, some nuclear reactors could be designed to like heat whole buildings, heat whole facilities, instead of just direct changing it to electricity. If direct heat would be required. All right, so let's dig more. I tried to find some helpful additional reviews to go over more details about small modular reactors that might be useful. So there was Emerging Small Modular Power Reactors, a critical review, the early 2020s. There's it reviewed smallness, modularity, and designs of SMR concepts, and at this point, there's over 100 reactor designs. So talked about smallness. Again, they're up to 300 megawatt electricity. They will need to rely on economy of multiples. That's analogous to economy of series. With modularity, that helps separate out functionality, reduces system complexity. So the overall system. However, one of the downsides I didn't think about until I read this is because if they need to be module, they can actually be over designed, so that can sometimes be a challenge. Now, some more details of the designs. We talked about the high concept designs, and I started to talk about some of the fuel and coolant. So this goes into more detail. So nuclear reactors need to be cooled. The currently operation large power plants use water cooling, but there's more experimental designs that can use gas. Molten salt is pretty common. Even things like liquid metal, like lead, or even other reagents, like I've seen reactors hypothesized for, like organic solvents. And then particle fuel. What sort of is the nuclear fuel setup? TRISO is a pretty common one. It could be again the pebble bed or embedded. You can have different types of fuel. We'll look at some of those details in a bit too as well. And the fuel actual composition. Now, obviously, uranium is typically the main one used, though. There's thorium reactors. I think that's outside of this topic for now. There's also reactors that can like burn things like plutonium, but typically these reactors are meant to do some sort of compound of uranium. And then how they're refueled, whether they're batched or online, or just meant to be sealed up and run for a certain amount of time before they're done, like a battery. So there's battery type. Other considerations is review covered, like safety. Breeder reactors actually make fuel for other reactors. Burners to actually burn off fuel from radioactive byproducts, and then some of the issues on licensing. And then another concept that I thought was helpful to bring up because it keeps coming up when you research these reactors is the difference between fast and thermal reactors. It turns out the difference is the speed of the neutrons. So the thermal is actually slower. The slower neutrons because there's a moderator such as water that slows the neutrons down. So light water reactors are the typical nuclear reactor working now, or a small modular reactor based on those designs are thermal. However, there are designs more like the Gen 4, which can be fast. So they have high speed neutrons, which means they actually have a wider range of fuel and burn out more, so they have less long-lived radioactive waste. But they take more design, and it's more of an experiment with the less developed, less mature technology. All right, another review: techno-economic analysis of advanced modular nuclear reactors. It was a bottom-up economic evaluation of small modular reactors. Looked at 12 77 megawatt electricity light water reactors, so like that new scale. Looked at 4 gas-cooled ones, so a little bit larger ones. 5 200 megawatt electricity molten salt ones, so again looking at a lot of the major coolant designs, and then compared to a large reactor and natural gas plant. And it looked like that the overnight capital costs were on par with a large reactor. So there's a figure here on the left. Here's a traditional nuclear reactor. We can see there's the light water, the gas cooled, and the molten salt. And they're sort of on par. The light water is a little more expensive, but the other two are a little less expensive. But they're certainly more expensive than natural gas plant with or without carbon capture. And then the levelized cost of energy is on par again with the large reactor. You can see here the levelized cost about the same. Again, the light water is a little more expensive, the other are a little less. But certainly they are more expensive than a non-carbon capture gas plant, even with a carbon tax. The red here is a carbon tax. If you build a natural gas plant for carbon capture, that's actually probably the most expensive. But if you're just looking at cheap, abundant energy, looks like natural gas still wins out. So there's that balancing factor between energy production and energy affordability. Now, one of the nice things, going back to comparing small modular with large reactors, is there's a lower economic risk compared to those associated with mega projects. Mega projects can often, their budget can explode, their construction time can explode, get much longer, it can even be canceled, and that's something like a large nuclear reactor is a mega project, whereas the small modular ones don't have as many of those issues. And so, in the end, small modular reactors remain economically competitive with large reactors, which benefit from economies of scale because of simplification, modularization, and construction time. Now, a lot of these, of course, are still projections because there's very, except in China and Russia, there are no small modular reactors uh, in operation. And of course, even if there were some in operation, those would be the those would be the first of their kind. It'll as things go on, it should get better. But that's sort of the economic realities that, yeah, they are competitive with large reactors at this time, in theory. All right, so kind of want to close by shifting to a very special type of small modular reactor, the microreactor. So I looked at this review of nuclear microreactors. And so they're a little bit different because they're not really conceived of as being the same use as large reactors, just on a smaller scale and like modular. They're actually used for something else. They're used for maybe individual industrial facilities, off-grid remote locations, military operations, national disaster recovery, and even space travel. And more specifically, so microreactor is a nuclear reactor with power output up to 20 megawatt electricity, maybe even 30, but it's much smaller and it can operate as part of a grid, off the grid, or part of our microgrid. And now, when it comes to technology readiness, this review looked at that. Uh, that scale goes from 1 to 9. Most designs are just at 4, maybe some moving up to 5. So again, they're in the design phase, they're conceptual phase. And there are no small modular, or there are no micro reactors, even in places like Russia and China. And there's different features. There's different reactivity controls, coolant choice, confinement of radioactive materials. Uh, Certainly, key advantage is very small size, simple layout, and fast installation. One of the challenges is limited fuel ability. Now, this goes into the types of fuel. Typical reactors use LEU fuel or low enrichment uranium, whereas some of the more viable or more useful microreactors, which is like can run longer, would need HALEU or like a high assay low uranium enrichment. So it has more enriched with uranium, but that's more dangerous and it's harder to produce. So there's sort of those issues there. Of course, there's security risk and licensing with microreactors, just like any other reactor. And now I really like this quote from the article. It should be, however, reminded that these claimed advantages should be proven by facts. It says no SMR is currently under operation. Now it's a little out of date for SMRs, but I think the point still stands. Is like a lot of this stuff is cool and interesting but it's speculative until something is actually under operation. We see how it works in reality, works actually to be commercially viable or not. And so this review had a nice table of some major characteristics of microreactor designs. They can run from anywhere through to 3 years without refueling to like 30 years. I mean, some of them are sort of meant to just almost be like a battery. More tables that had some nice overview of the different designs. Microreactors, like small modular reactors, can be cooled by different things like liquid sodium, helium, light water, helium. Have different power conversions, different fuel like trisol or UO2, etc. And then there's table 7 was nice about comparison because really what microreactors would be compete against is something like diesel generators in a remote location or renewable sources like solar or wind. And so, and I think, the electricity generation costs are sort of on par with those two. I think some of the renewables is skewed because, like, I don't think they actually built in the fact that you actually need backups. So I don't think these numbers are quite correct, but certainly with the diesel generators, it's on par. Now, some of the capital costs are more. That's one of the big downsides, but overall, electricity generation, I think, is on par at least initially. All right, another review of microreactor reactors, prospects for nuclear microreactors. Major of the study was actually the deployment potential across global markets. So they're a subset of small modular reactors. We talked about that before. Now, obviously, there's commercial and operational uncertainty along with regulatory gaps, and so that's hampered adoption. Now, some really important details that I liked from this review is talking about capacity factor. That's an important thing for energy. Nuclear in general has a great capacity factor, over 90%. And even things like natural gas or coal has 57 or 48%. Not nearly as good. And then hydropower, even and wind and solar even worse, very low capacity factor. That's one of the things that hampers renewable energy is sure, maybe you can get it going, but then you need backups because it doesn't have a high capacity factor. Operational period, nuclear, at least regular power plants can be 40 to 60 years, so that's a pretty long time frame. Whereas gas is only 20 years, a gas plant, coal plants 40 years, wind and solar are only 20, 25 years. So nuclear reactors, maybe not microreactors, which typically have a shorter life cycle, especially if they're the battery type. Um, but nuclear energy has a pretty good lifetime. An important point is that, yeah, initially microreactors are really competitive in places where they would replace diesel fuel generators. And this review talked about different profile markets of where these microreactors could really be useful. Isolated operations, distributed energy, resilient urban, disaster relief, and marine propulsion. And they also calculated relative market scores across regions. So they had a table, different microreactor designs and technical specifications. We've seen things like this before, but it's also always helpful to see. We see, General Atomics, we have new gen, new scale, um, nano, etc. have different setups with different fuel types, coolant, moderators, refueling intervals, etc. And now, again, I really like the different profiles. There's isolated operations that's probably the most go-to. You have a remote mining center or a remote village. You're able to get energy out to them. Distributed energy help sort of support an energy system, especially if it's spread out, maybe more in the rural areas. Resilient urban, that's helpful as you think of like these cities get bigger, it's hard to get power out to the outskirts. So having small mod or micro reactors might be useful in bolstering that. Disaster relief, being able to have like a mobile power plant, essentially, maybe on the back of a truck that can drive in where normal power is knocked out, or even looking at critical services like desalination. And then finally, marine propulsion, actually having ships powered by uh, micro reactors. I mean, of us, we have nuclear submarines, so that's not a crazy concept. And while that Russian ship, the academic Lomonosov, has a small modular reactor, it's not actually to power a ship. But you can imagine ships not having to burn all this diesel fuel because they're powered by small modular reactors, specifically of the micro reactor type. And then here's the profile scores by region. Some regions are more amenable to that microreactor um, markets. All right, just some examples of microreactors to kind of close out here. There's Halogen, has this Hollows generators microreactor, like a motor, a couple core generator, and because it's so small, it could fit in a standard ISO container, shipping container. So that's pretty cool. So very, very mobile. There's Westinghouse Electric Company's eVinci microreactor example here, concept here. And I think one of the coolest one is the nano nuclear energy. Has their Zeus, which is, a reactor built on the back of a truck and it can be just driven wherever. They also have other concepts. I think Kronos is sort of a built underground one, so a more typical reactor. And then Loki is a reactor built for like space travel. All right, so one of the big questions I get through this is like, well, these look really great. They're really interesting, a lot of concept out there. Why aren't there any small modular reactors in the US where I'm based? So I actually asked Alex AI. It's AI based on the writings of Alex Epstein, a big advocate for energy abundance. So I actually asked the question, why haven't small modular reactors been built and deployed in the US by now? Now he says the short answer is they haven't been built because of political and regulatory hostility combined with market and technical bottlenecks that make them uneconomic and slow to reach commercial readiness. Not because the technology is in itself unworkable. There's just too many hurdles right now. The longer answer is that essentially U.S. policy and permitting system has criminalized fast, affordable nuclear innovation through things like overregulation and fractured permitting, political and activist obstruction, economics and financing realities, supply chain and technical constraints, and market uncertainty and canceled projects. So So they are viable if a lot of like the regulatory issues and other things hamper it could be let out of the way so that innovation can be tested and actually deployed. All right, with that, hopefully this was an interesting spotlight. Here are all the references I have. You can look at them in more detail. And with that, thanks for joining me. Please like, subscribe, comment, especially comment what topic should I cover next. With that, I'm Mark Williamson. Thanks for joining me. Have a great day.